Hi everyone. In this section, we're going to be working to understand a number system that broadens the real numbers to what we call the complex numbers. We really want to be able to sort out what makes complex numbers a little bit more unique than the real numbers, and then also understand some different properties in math and algebra involving complex numbers as well. So to begin with right here, we're going to take a look at these three functions right here that are all quadratic functions whose graphs are of course parabolas. And our motivating factor here is to try to find what the zeros are for each of these three different types of functions. So we'll start with this function that you see right here of y equals x squared minus 1. So if we're trying to find the zeros of the function, we of course have to be able to understand what the definition is for a zero of a function, which is defined as making the output value equal 0. And then the x values would be the actual zeros that when you plug in those x values makes the y equal to 0, right? So on a graph, you'll be able to find zeros of the function on the x-axis if they're going to be real zeros, because like at this point right here, you've got 1, 0, which means that the output value there is 0, and so then the corresponding input value would be 1, and then also right here you've got negative 1, 0. So what I've labeled there are the x-intercepts. What the zeros are themselves are just the input values, or the x's. So the zeros of this function are just going to be both the numbers 1 and negative 1. Okay? So then, of course, when you look at the next graph, you'll see that there's only really one x-intercept, and so the only zero that we can easily identify from that graph right there is just 0 for x, which then coincidentally also gives you 0 for y, right? So in both of these examples, you can easily like plug in these numbers. So if you plugged in 1 in for x and then you plugged in negative 1 in for x, you'll find that 1 squared minus 1 does equal 0 for y, and negative 1 squared minus 1 does equal 0 for y. And then also if you plug in 0 for x right there, and 0 squared is going to equal 0. So it all works, right? And then we run to this last little interesting little fella, right? So when you look at the graph of that parabola, it's x squared but plus 1. So of course the graph is shifted up 1 unit. And there is no place where it ever crosses the x-axis, of course. So what we would probably guess then is that there's going to be no zeros of this function, so nothing that we would be able to plug in for x. And if we were to like try to figure out a way from the equation to be able to make the y equal 0, we could set up this equation and then try to solve it for x. And then if you subtracted 1 from both sides, negative 1 would equal x squared. But if x were positive, squaring it would be positive, and if x were negative, squaring it would also be positive, which means it can't equal a negative, right? And so there turns out to be no real number zeros for this graph because it never crosses the x-intercept. But there actually are two zeros for this function that are non-real zeros. And this is really where we want to start getting into this notion of complex numbers and imaginary numbers, because that's what we need to understand what the zeros of that function actually would be. So we're going to start by defining imaginary numbers and some simple properties of imaginary numbers, first of all, here. So when we call imaginary numbers imaginary, we're not making them up, right? It's just we would call them imaginary numbers. So they're real in the sense that they actually exist, right? We actually use them, and they're super important. Lots of physical applications of engineering, electricity, whatever it might be, right? So the imaginary unit actually comes from defining, first of all, this, that when we pick some number I and we square it, it equals negative 1. Okay, and this is how we first start defining imaginary numbers. So from there, if we take that equation that I just defined where I squared is equal to negative 1, and then I like square rooted both sides, that would basically just solve it to get only the number I alone, right? Then that would lead us to the conclusion that I would equal either positive or negative roots, but we're just going to go with only the positive root right here. That I is going to equal the square root of negative 1. And this right here is exactly what your imaginary unit is. So what 1 unit's worth of an imaginary number is that it's the square root of negative 1. So really at its core, imaginary numbers are going to come from taking a square root of a negative number. Okay. So in the next slide, we're going to look at some ways that we can simplify some different types of square roots that have negatives underneath them. So we just need to understand one quick property about that before we can do such a thing. So if we have that n is some positive number, some positive whatever, then when we do the square root of negative of that positive number, so what that really just means is then under the square root, we truly have like a negative quantity overall because n was positive, right? So now we've got negative and positive, which is a negative. Then this is equivalent to taking out the -1 as a factor under a separate square root. And so that comes from properties of square roots that we already know is true. And then because we now know that the square root of -1 is equivalent to I, this is just equal to I root n. Okay. So I kind of showed the proof of that. Really what's important there is just to recognize that when you have the square root of any negative number, then you can just write it as I root of the positive number, right? So for example, if you've got negative like 3 underneath a root, that's just the same thing as I root 3. Okay, so that's all that's saying. So now looking at some examples here where we want to simplify some complex or imaginary numbers. So you see here that we're asked to simplify each number by using the imaginary unit I. Really, it's just saying get these roots into simplest radical form. So you're really not allowed to keep negatives underneath square roots. So you got to get the like negative outside of a square root and then write it in terms of I. Okay. So for the very first example right here, you can easily just write this as I root 6 because of the negative that's inside of that root. And then you have to ask yourself after that point, can I simplify the root 6 part of that? So are there any perfect square factors that might go into that 6? So like 4, 9, 16, 25, etc. are going to be perfect squares. None of them are factors of 6 because the only factors of 6 that are not 6 and 1 would be 2 and 3, right? And 2 is not a perfect square and 3 is not a perfect square. So this gets it into simplest radical form. Okay. With this one, it does have a negative underneath the square root as well, so you can write this as I root 169. And then 169, hopefully you're aware, is a perfect square, so it's actually just I times 13, but we'll preferably just write that as 13 times I. Okay. So what you should notice about actually both of these examples we've done so far is that both of these are really like actually positive numbers, right? So even though you have a negative under a root, that doesn't make the number negative. Okay, so both of the numbers we've had actually are positive imaginary numbers. So that's really, really critical. Okay. With this example right here, you've got two different negatives. You've got a negative in front of the root, and then you have the negative inside of the root. So you cannot take a number that's outside of a root, multiplying with it, and multiply inside. Just doesn't work ever in math with anything. So you're not able to do like a negative negative and make this positive at all. So what you'll just need to be able to evaluate separately is evaluate that square root separately or simplify it separately. And then that negative that's in front is just going to make it negative. Okay. So in the yellow, we have the square root of -4. So because you're square rooting a negative, of course, we know that it's going to be I root 4, and then multiplied by that -1 in front of it. And then 4 also happens to be a perfect square like 169 was. So it just ends up being 2, and then I, and then negative, right? So this is the first example that we've seen so far on this slide that we actually got a negative imaginary answer, right? So really the only way that a imaginary number that's expressed in a square root form could be negative is if there's a negative in front, right? All right, and then for the very last example right here, you've got negative of the square root of 72. So because inside of the square root, you actually have a positive radicand right there, this is actually a real number. This is something that you could plot on the real number line. So this is not an imaginary number at all. Now, when you want to simplify this number, you have to look for perfect square factors that would go into 72. So does 4 go in? 4 does go in. And then 9 also goes in. So actually, because both of those go in, then 4 times 9 should go in, which is 36. That's what you would preferably want to do, right? So 16, 25, 36. And 36 ends up being the biggest perfect square factor. So if you write this as square root of 36 times, and then to get to 72, you have to multiply 36 by 2. This would be a simpler form of the expression, and then you can root the 36 to get just the whole number 6 multiplied by root 2, and then you have the negative right there. And so this would actually give you the simplest possible form of that number, but there's no I, there's no imaginary stuff happening right here because you didn't have a negative underneath of that square root. Okay? All right, so that gives you some context in terms of simplifying imaginary numbers there. So just even more general than imaginary numbers is what we call the number system of the complex numbers. So before we talk about the complex numbers, let's just recall a little bit about what you already know about the real number system. So when we're talking about real numbers, these are actual numbers that you can like tangibly use to like measure certain quantities. Like if you were measuring like the length of a piece of lumber, like you could tangibly measure that as having like a measure of 36 inches or like some even weird, funky, irrational number like pi inches long, right? And then even like negative numbers, you can measure like, how much money you have in your bank account or something might be negative, right? So real numbers are just really any number that belongs to the real number line, like 0 is a real number, the square root of 5 is a real number, negative 2 pi is a real number, 3/8 is a real number, 1 million is a real number, okay? Anything that belongs to that is called a real number. And then hopefully you've learned how we can classify and break up real numbers into different sorts of types. So you have the real numbers that are rational, so numbers that can actually be expressed as a fraction. So things like 3/8 or -5 and 1/17, etc., or 0.083 repeating. So if the decimal goes on forever, it's got to have some sort of repeating pattern if it's rational. And then also if like the decimal stops, like 0.741, then it can be rational as well. And then you have the irrational numbers, and those are numbers that cannot be expressed as a fraction. So if you have something like 1, 0, 2, 7, 4, 3, 8, 1, 9, it just like goes on randomly forever, then that's going to be irrational. And even if it has like a pattern, but it doesn't like repeat the same chunk over and over and over. So you can see there's like a pattern right here, but it doesn't repeat the same chunk of like 4 digits over and over, or the same chunk of 1 digit over and over, the same chunk of 39 digits over and over, right? It's going to be irrational. So some other common numbers that are irrational would be like pi, doesn't have any repeating patterns. And then also like square roots of non-perfect squares. So square root of 2 and square root of 3 are going to be irrational, but not the square root of 4, because the square root of 4 is 2, which you can write as a fraction, because you can write it as like 2/1. And then you could do like 5, 6, 7, and 8 under a root, because none of those are perfect squares, but you have to skip root 9, and then you skip root 16 and skip root 25, right? All those are going to be rational. And then going back over to the rational numbers, you have what we call integers, which are just numbers without decimals. So like -3, -2, -1, 0, 1, 2, 3, and then going backwards and forwards from that are integers. And then whole numbers are numbers that start at 0 and then count up and don't have any decimals. So whole numbers can't be negative, they just start at 0. And then finally you have the natural numbers, which start at 1. So whole numbers and natural numbers are almost the same. It's just that whole numbers include 0, but natural numbers exclude the 0, right? Okay, so those are real numbers, and those are the numbers that, for the most part, you've used mostly. And so we are going to now start using complex numbers quite a lot. So when you have a complex number, basically complex numbers are just numbers that can be written in a certain form. So complex numbers are going to be numbers that are in the form a plus b times I, where both A and B are going to be real numbers. So when we say that A and B are real numbers, like literally, they can be any real numbers. So A could be square root of 2, and B could be negative 5/3, right? Just real numbers, and then I, of course, is the imaginary units. Okay. So when you start breaking up the complex numbers, you can break up complex numbers into kind of two different parts. Complex numbers that are actually just purely real, and then complex numbers that are like purely actually like complex. So when we have real numbers, a real number would just be like only the A part of A plus BI, which means that B would have to equal 0, right? So if B was 0, to get rid of the imaginary part, and you have only the A part, that's just a real number, okay? And then purely complex numbers would have A plus BI, where A and B both do not equal 0. So you do have some A part that actually exists there, and then B actually exists right there. And then you can have what we call pure imaginary numbers that have only the imaginary part, so have only the I part. So that would basically mean that the A is going to equal 0, but then the B part is still going to be there. So if you had like 5i or negative root 3i or something, those are pure imaginary numbers because they have only the imaginary part versus like up here, if it was purely complex, you have to have like 1/2 minus I, where you have both the real number and the imaginary part, right? And then, for real numbers, there's just got to be like 3 or something, right? That doesn't have an I with it. So in general, when we're talking about complex numbers are numbers that include all of the real numbers with them, but also the possibility that we could be plusing or minusing some other imaginary component to it. Okay. So right here you see this family tree, and what's filled in already is the family of the real numbers in terms of how we can break them down. So I exemplified that for you. You'll see in the gray boxes like the different symbols that can get used to represent the sets of these families of numbers. So if you ever see those kind of fancy little symbols, that's what we're talking about there. So from the numbers that are just like purely um, complex numbers, so that have like the A plus BI structure that at least have the I, and then you also have the pure imaginary that could probably fall underneath that. So we could probably add like another box, right, for the pure imaginary numbers. When you put together real with those purely complex numbers, we get the family of numbers that are called the complex numbers. And really what you want to understand about complex numbers is we'll represent them with C, and yeah, that's what complex numbers are. Have real numbers and imaginary parts to them. Okay, so we're going to spend the rest of our time in this section here dealing with some just basic algebra and characteristics of complex numbers. So the first thing that we're going to dive into right here is talking about the graphical perspective of complex numbers. So when you are graphing functions, your previous experience in graphing functions has been to graph functions on an xy plane when you're relating two different variables. But the thing is that you've always been using both of these axes as real number lines. So the x-axis was representing real numbers and the y-axis was representing real numbers. So to be able to represent complex numbers, we have something that's called the complex plane, where the horizontal axis is going to represent the real component of your number, and then the vertical axis is going to represent the imaginary component of this. Okay, so the complex plane is really useful for graphing numbers. And when I say we're graphing numbers, we are really only graphing numbers when you graph a single point on the complex plane. You're not actually graphing a point. And here's how you'll see that. So if we're going to say, like, take this complex number right here of 3 plus 7i and graph that, all you would need to do is match up 3 on the real part with 7 on the imaginary part. And then that location right there, it's not a point, so it's not an ordered pair. We're not going to like put parentheses like you put an xy point. That's just where the number 3 plus 7i is going to go on the complex plane. Okay, so if you had like, say, this point right here, that point is only on the real axis. It doesn't have an imaginary component to it, so that's just the number -6, right? And then if you had like right here, this point right there, that's only on the imaginary axis, so it doesn't have a real component to it. It's just purely imaginary. This would be the number -3i, right? So it's like the same as graphing points, right? It's just like the x number, what you'd normally think is corresponding to the real component of the number, and then the y component is corresponding to the imaginary component. But ultimately, all those points that we just graphed are just numbers, right? All right, so we're going to skip ahead to this section right here where we'll do adding, subtracting, and multiplying and dividing with complex numbers. So I don't need to fill in what's at the top right there. We just need to look at some examples right here. So when you're looking at this kind of a problem, it looks like you have 4 separate terms, but what I need you to understand about this is that there's not really 4 different things right here. You're actually really just adding 2 numbers right here. Because when you look at this right here, this is actually a complex number. It's of that form a plus bi. And then you look at this number right here, that's also a complex number. So it's really just take a red number and add the blue number, right? Because of the plus sign that's between. So when you're plussing, you're just adding stuff together, right? So we really just need to combine like terms. So in actuality, like the parentheses are pretty much useless other than the fact that they're just emphasizing you have 2 different numbers. So it's literally equivalent to just -10 minus 2i plus 6 minus 3i. And then you can just combine the like terms, and you'll just want to put the real stuff together and then the imaginary stuff together. So the -10 and the positive 6 you want to combine together, and that's going to equal -4. And then the -2i and -3i you'll want to combine together. -2 plus -3 is -5, so you end up with a combined total of -5i. And that's the way that you'll want to express your answer. Make sure that your answer is always the real number expressed first, and then the imaginary number expressed second, so that it's in the a plus bi form. And then that's going to be your final answer for the sum of those 2 complex numbers, okay? And then here, this is actually really, at its core, just a subtraction problem, because you're subtracting the second grouping from the first grouping, right? Now, when you look at the first grouping of numbers right here, you have -√64 plus root of -9. So this first number right here is really just negative of the real number 8, because you've got a positive 64 under the root, right? And then plus, and then right there, because you've got the negative under the root, that's going to be imaginary, so you need to think about this as being equivalent to I root 9, and then the root of 9 is 3, so it's really just -8 plus 3i. Subtract, and then in this other grouping that you've got over here, you've got negative of root 8. So because you've got root 8, you know that there is the perfect square factor of 4 that goes into 8, and then 4 times 2 is going to give you 8. So when you root the 4, you just get a normal 2. So 2 root 2 would be the simplest form of that. And then, of course, you do have the negative right there, right? Plus, and then with this fella right here, you do have the negative that's inside of the root, which means that that's going to be an imaginary number, right? So it's going to be I. And then if you had the root of 4/9, the root of 4/9, both 4 and 9 are perfect squares, right? And so square root of 4 is 2 and square root of 9 is 3. It does end up being 2/3 because 2/3 squared, 2/3 times 2/3 is 4/9, right? So then that is actually just equivalent to plus 2/3 I. Okay. And then, yeah, then we just really need to combine like terms, just realizing that subtraction needs to distribute to that whole grouping there. So we're going to ultimately end up adding 2 root 2 and then subtracting 2/3 I once that subtraction distributes. And then you'll want to combine together the -8 plus the 2 root 2. You won't be able to add those together because they're not really like radicals or anything like that. So that's just going to be -8 plus 2 root 2. And then just for emphasis, I'll put that in parentheses so we know that's like the real component. And then right here, you'll want to add together 3i with -2/3 I. Those you should be able to put together. You'll just like need to get a common denominator to figure out what your coefficient would be for the I. So your common denominator is going to be a 3. So you'll need to get that 3 also have a denominator of 3. So just 9/3 I minus 2/3 I then. And that'll end up being 7/3 I. So plus 7/3 I. That will be it for your answer that puts it really into your A plus BI form. Great. Okay, so let's get into multiplying then. So, in order to understand multiplication of complex numbers, there's one thing that we need to understand first of all, and that would be multiplying powers of I. So, we're going to start off by denoting what I is equivalent to. And I did put it in the second row purposefully here because I'm going to put something before it just a little bit. So, I'm just going to say is equivalent to I, just for now, but just rather than a because, let's just note that we should know that I is equal to root of -1. That comes from the definition of the imaginary unit from before, right? So what I'm going to do next is I'm going to try to figure out what we get when we start multiplying I with itself a bunch of times. So first we're going to investigate what we would get if we did I times I. So if we were to do I times I, like that would just basically mean that we're doing root of -1 all squared, right? Which gives you -1. And that actually came from the definition of the imaginary number from before. If you remember, I said I squared is going to equal -1, right? So I squared is actually equal to -1. And then if we were to look at I to the third power, that would mean I times I times I. But the first couple of i's right there would be I squared, which we know is -1. So it ends up being -1 times that third additional I, which ends up being -I. So I to the third is actually the same thing as -I, right? And then I to the fourth would be I times I times I times I. And we know that two of them together would be I squared, which is -1. And there's another pair that we have right there. So we really would have a -1 times a -1, which would just equal +1. 1 times 1 is 1, and negative times negative is positive, right? So therefore, I to the fourth is just equal to 1. And then if we had I to the fifth, I to the fifth would mean I times I times I times I times I. And then one identity that we just discovered here is that if we multiplied 4 i's together, I to the fourth is going to equal 1. So we really just have 1 times I, and 1 times I is just going to equal I, right? And you'll see that right here now, we just got back to where we were at when we were at the first power. And so then if we were to go and do this now to the sixth power, the first 4 i's of here would just become 1. And so then we would just get 1 times 2 more i's. But 1 times anything just keeps whatever the 2 i's equals, which would just be I squared, which is -1, right? So we start seeing just kind of this circular pattern going through the same 4 numbers over and over and over and over. And that's truly what's going to actually happen. So when you do powers of I, you just circle through the same numbers over and over and over and over and over, right? So when you start at the first power, when I to the first is equal to I, that actually starts right here. So this is going to be I to the first power, which is just I, of course. And then from there, we got -1 as I squared. And then we got -I was I to the third power. And then we got I to the fourth is 1, right? And that's actually where they would be graphed on the complex plane, because this is where I would be, right? This is where -1 would be, and this is where -I would be, and this is where 1 would be, right? So it just goes in this circular pattern, actually graphically, if you think about it that way, as you do powers of I. Okay. One last thing just to mention here too is that when you do I to the 0 power, it is going to equal 1, which fits into the pattern that we're seeing here of alternating between the same four numbers circularly. And then also, whenever you raise something to the 0 power, it's just going to equal 1, which you know to be true as well. So taking that then, we want to try to be able to simplify each of these expressions right here and try to figure out what their values would be. There's really not a way that a lot of your calculators actually can be able to like figure this out, right? So you have to really be able to understand multiplication and powers of complex numbers. So to really figure out and understand these problems, let's just go back to where we were right here and just kind of notice some patterns that we were seeing here. So you'll be able to see that because we were going through a pattern of the same four numbers over and over and over and over, that then really comparing what the exponent is right here to the number fours is really critical. So right here, when we had I to the first, okay, that 1 divided by 4 is equivalent to a decimal of 0.25. And so if you take any power of I and you divide it by 4 and you end up with a decimal of 0.25, it's really just going to correspond to I to the first. So like, for example, let's say we wanted to figure out I to the 45th, let's say. Well, if you took 45 and you divided it by 4, you're going to get 11.25. And then because of that 0.25 remainder, which is like 1/4, that tells you that I to the 45th is actually equal to I to the first. And so then it just simplifies to I. And then that's a similar thing that you'll see for all the rest of these. So when you have I squared, so I squared would be related to like 2/4, which has a decimal remainder of 0.50. So any exponent on I that's going to have a 0.5 remainder, it's really just going to correspond to a value of I squared. So like, say that you have I to the 38th power, right? Well, then that would just be the same thing as 38 divided by 4 is going to give you 9.5, right? And then it ends with 0.5, so then it's just got to be the same thing as I squared. And then if you had I to the third, that's going to be like a 0.75 remainder when you have 3/4. So if you have, say, like I to the 11th that you wanted to figure out, we know that 11/4 is equal to 2.75, which ends with 0.75. So I to the 11th is going to be equal to I to the third, etc. Right? So anytime that you end with a decimal of 0.25, right, it's going to be the same thing as I to the first because 0.25 is 1/4. 0.5 is going to be the same thing as I squared, just like 2/4. And then anything that ends in 0.75 is going to be I to the third. And then anything that ends with 0.00, so just divides evenly when you divide by 4, is going to be the same thing as I to the fourth, which is actually just equal to 1, right? And then, of course, you want to express this as a -1, express this as a -I, so you get them in their most simplest terms, right? So that's whenever you divide the exponent just by 4, right? So it's really simple. So if you have I to the 14th, just take 14 divided by 4, and when you do so, you're going to get 3.5. Okay, great. So it ended in 0.5, which means 2/4. So then this is going to be equivalent to I squared, because 0.5 is 2/4, so that's where the 2 is coming from. And then you just need to know that I squared is equal to -1 from the definition of imaginary numbers. So that's what I to the 14th is, -1. So you need to express it in that simplest form. If you have I to the 95th, do 95 divided by 4 and see what you're going to get. In that case, you're going to get 23.75. Okay, so it ended in 0.75. 0.75 means 3/4. 3/4. So this is the same thing as I to the third then. And then you just have to know that I to the third is equivalent to -I, and then you're done. I to the 777th, right? If you do 777 and you divide it by 4, It's gonna be somewhat just shy of 200, so it's gonna be like 195.25 or something. I think that's right. But anyways, it ends in 0.25, which then means that it's equivalent to I to the 1/4, because 0.25 would be 1/4, and then I to the 1 is just I. So there you have it, right? And then the last one right there is I to the 525,600. If you take 525,600 and you divide it by 4, um, I don't know, it's going to have some answer, but whatever answer it is, it's going to be whole because it just ends in 0.00. So it's just a whole number. So because it did so, that's the same thing as like either I to the 0 then, because it'd be 0/4, or I to the 4th, because it'd be like 4/4. Regardless, it's just going to equal 1. It divides evenly, because that's what I to the 4th is, or what I to the 0 is ultimately. Okay. So with that, then we can really truly understand multiplication of complex numbers, because we need to understand powers of I. So when you're looking at this first example right here, we're asked to write each product as a complex number. So we're asked to write the square root of -49 and multiply it with the square root of -16. So one thing that you can't do with complex numbers that makes it a little bit different than real numbers is you can't multiply the two numbers together underneath the same root. So one thing that we know to be true is that if you had, let's say, the square root of 2 multiplied by the square root of 5, you can say that is equal to square root of 10. So if those two numbers to begin with underneath the square roots are both positive, then you can multiply them together under the same root. It's not going to work when the two numbers underneath are imaginary. So I will explain so you can really see why that would uh, cause two possible different answers is really the reason why. So what would be the correct way to go about this then? Is to actually figure out what these numbers are individually. So if you have root of -49, it's going to be imaginary times 7i. And then right here, this would be 4i. And then we'd have to multiply them together. So 7 times 4 would be able to multiply together to be 28. And then I times I also have to multiply together to become I squared. Whenever you are writing a complex number answer, it always needs to be in a plus bi form. And so part of that then would mean that if it has to be an a plus bi form, you can't have an exponent on the I when it's in simplest form. So we need to change that I squared to a simpler form. So we know that I squared is equal to -1. So then we have really 28 times -1, which is going to be -28. So that's the correct answer for the simplification of this expression, okay? So what would be wrong, this is how I started off by explaining it, this is like to try to multiply the numbers together underneath the same square root. So if you took -49 and then also multiplied it with -16 under the square root, then you'd have a root of some positive number, right? And then once you like rooted that really big number, you would end up getting an answer of 28, which is like, close to what we had before because we got -28, but the answer needs to be -28. So that's why we can't use that same property, the product property of radicals with complex numbers, because then it gives you a positive answer and it's not supposed to be positive because you're actually really taking an imaginary number times an imaginary number. So we have to go about it in this way when we're evaluating such expressions. Okay. Okay, the rest of these are going to be pretty straightforward, just in terms of like the algebra involved. The only thing that's new for us is just understanding the imaginaries and how they play out here. So with this expression right here, it's really just a distributive property, right? You can multiply the 5i to both of these terms. This is going to become -15i. And then when it distributes to right here, 5 times -6 is -30. And then make sure that when you distribute the I to something that also has an I, you write the appropriate exponent. So it's going to be I squared. Now we know that we can't leave an exponent on that I, so we'll have to change that I squared to become a -1. And then you'll be able to multiply the -30 with a -1 to become a +30. And then you don't want to leave it in that form because the I term is first and then the real number is second. So you'll just want to switch the order around So this expression is, of course, equivalent. That way you write it truly in the a plus bi form, of course, right? And then with a simplification like this looks like foiling, right? Because you're multiplying the two groupings, and that's ultimately how you'll want to go about this. It's really just FOIL it. So 9 times negative 8 is going to give you negative 72. And then 9 times 3 is going to give you 27i. And then 4i times negative 8 is going to give you negative 32i. And then finally, 4i times 3i is going to give you 12i times I, which is 12i squared. Right? So then from there, any simplifying that you can do, combining like terms, what have you, right? So one thing you'll definitely want to do is take care of that I squared and replace it with a negative 1. That means you're really going to subtract 12 at the end right there. And then these couple of things you can put together because they're both I terms. So 27 minus 32 is negative 5i. Still have this negative 72 in front, but then you'll want to be able to combine together these couple of numbers since they're both real numbers. Negative 72 minus 12 is negative 84. So then you just get a final answer there of negative 84 minus 5i. All right, and then last of all right here, with an expression like this, you'll see that you've got the negative I root 6 that's multiplying with the quantity of the parentheses all squared. So by order of operations, by PEMDAS, you can't distribute the negative I root 6 in front yet. You have to be able to do this part here first, in the yellow, because it's exponentiated, right? Exponentiation has to happen first. Now, in order to do this, where you've got a subtraction of two numbers, it has to be FOILed. So you have to actually write this out a couple of different times. So 12 root 3 minus 5 fourths I, and then times 12 root 3 minus 5 fourths I, right? Okay, so let's carry out the foiling then. So we'll have to do 12 root 3 times 12 root 3. So you can times the 12 with the 12 to get 144. And then root 3 times root 3 is just going to be a normal 3. So you get 144 times 3 there. And then when you do this part of the FOIL, you'll have 12 root 3 times 5. 12 times 5 is 60. So it's minus 60 root 3 all over 4. And then also the I. And then this part of the FOIL is going to give you the same thing because it's a negative times a positive as well. So it's minus 60 root 3 over 4i. And then the last part of the FOIL here would be negative 5 fourths times negative 5 fourths, which will be a positive. 5 fourths times 5 fourths is 25 sixteenths. And then also I times I is I squared. Okay, so all of that is going to eventually get multiplied by the negative I root 6 in a little while. So we can simplify in the parentheses quite a little bit of stuff. So you should notice that right here, 60 is visible by 4. It's actually negative 15. So negative 15 root 3i, and that's also what that is. So you're going to end up with negative 30 root 3i. And actually, we normally write the I before the root when we have such expressions. So that form would be preferred. And then if we replace this right here with like a negative 1, then it's really just subtracting 25 sixteenths. And then you'll be able to add together this 144 times 3 with the negative 25 sixteenths. So it's 432 is the 144 times 3. And then you'll subtract the 25 sixteenths. You can turn it into a fraction. It's kind of a crazier fraction. So I just used my calculator here. Came up with 6,887 over 16 minus 30i over root 3, of course. And then all that needs to be multiplied by the negative I root 6 then and distribute. So when this distributes to here then you get 6,887i root 6 in that order multiplied by a negative. And then when you distribute to here, you're going to have a negative times a negative, so a positive, and then your 30, and then you do have an I multiplying with an I, so it becomes I squared. And then root 3 times root 6, because there's both positive numbers underneath the radicals there, then they can multiply together under the same root and become root 18. And then we can do some simplifying. So the second term right here, so this term right here, has the I squared, which we know is negative 1. So that makes it actually now become subtracted instead of added. And then that term that's circled actually becomes real. So I should actually write that term first as negative 30. And then root 18 can actually be simplified too, because you can write that as root 9 times root 2 to simplify that. And then root 9 is 3. So the 3 will be able to times with the 30 to then become 90 with that root 2 that's going to be left. Okay. And then the other term that we have right here is that expression there. And you can't simplify that. There's no perfect square factors of root 6, and there's no exponents on I or anything. So this is going to give you the simplest possible form for that multiplication happening there. Great. So for dividing of complex numbers, to understand division of complex numbers, we need to be able to understand complex conjugates. So to define that, we can say that the complex conjugate of a number that is a plus bi is a minus bi. So all that we've done there is really just taken the imaginary part, the bi part, and switched it to opposites, right? So the math that happens with complex conjugates turns out nice specifically when you're multiplying two conjugates with one another, because it's always going to turn out to be real. So like, let's say that you have negative 3 minus 2i as a complex number. So its conjugate would be switching the sign of just the imaginary number. So we would be plussing 2i instead, but the other number would stay the same. Okay. If you then take those conjugates and you multiply them with each other, and you FOIL, you'll get 9. And then negative times positive is minus 6i. Negative times negative is positive 6i. And then negative times positive is negative 4i squared. And you'll notice then that these right here are going to cancel out, leaving you with just 9. And then if we replace that I squared there with negative 1, then you end up adding 4. So you end up getting an answer of 13. So it turned out really, really, really nice for us. So we could kind of generalize that and say that if you have a plus bi multiplied by a minus bi, it always does turn out super, super nice, because you'll get a squared and then minus abi and then plus abi and then minus b squared I squared. But then these are going to cancel out. And then if you replace that I squared there with a negative 1, you end up adding. So it actually turns out that when you multiply two conjugates, it's actually the sum of the squares of the coefficients of a and b then. So that helps us to divide complex numbers. So these are all division problems, right? So we're asked to divide and then express each quotient or the answer to the division problem as a complex number that is in standard form. So that just means this, right? A complex number in standard form would be a plus bi. So to do this division problem right here, and whenever you're dividing complex numbers, you're not going to like divide in the way that you think you should. The way that we're always going to divide complex numbers is we're going to multiply by 1, but in disguise. So we literally will do this, multiply by 1, and when you multiply by 1, of course, then the expression still has the same value, keeps it the same, right? What you're actually going to multiply by, though, is you're going to multiply by a fraction where both the numerator and the denominator are the same quantities. And what you'll want to use is you'll want to use the conjugate of the denominator of this original quotient on both the top and bottom of this fraction. So since your denominator is 3i, or in other words, 0 plus 3i, its conjugate would be minus 3i with the 0 still the same. So in other words, you're just multiply by negative 3i to both the top and the bottom. So what happens then is the denominator will no longer have an imaginary number on it, because you end up getting the negative 9 times I squared in the denominator, which then turns into negative 9 times negative 1, which is a positive 9, right? And then you just got to like distribute in the top part right there, the negative 3i. So that becomes negative 27i And then negative 3 times 12 is negative 36. And then I times I is I squared. Yeah, so you just get negative 27i. And then since I squared is negative 1, it becomes plus 36. And then you can write this in a plus bi, so in standard form, because it's really just 1/9 of 36. So it's 36 ninths minus 27 ninths of I. And then you can actually reduce both of those fractions because 36 divides by 9 to become 4. 27 divides by 9 to become 3. So then we get an answer there of 4 minus 3i. So when you see this problem right here, it's just written as division. You can think about it as just 5 divided by negative 6i, of course, right? So you'll want to multiply it by the conjugate of the denominator, by both top and bottom, right? So since the denominator is negative 6i, its conjugate would be 6i. So you're going to multiply both the top and bottom by 6i then. So the top's going to become 5 times 6i, which is 30i. And then right there, the bottoms will multiply. Negative 6 times 6 is negative 36. I times I is I squared. And then you can replace the I squared with negative 1. Negative 36 times negative 1 is 36. So you get 30i over 36. And then you'll be able to reduce 36, because they both divide by 6, to become 5 6i. And then that's your answer for 5 6i. Okay. And then finally, with an expression like this that you want to try to simplify, you don't want there to be any imaginaries in the denominator. It's not considered its simplest form, so we need to do this division. And the way you'll do this is you'll multiply by the conjugate of the denominator to both the top and bottom here. So you'll need to make it become plus 2i instead to change the sign of the imaginary part, and then keep the real number the same as a negative 4. And then you're just going to have a whole bunch of foiling, right? It's the foiling that happens here where you're actually multiplying conjugates that you'll get the first times the first to stay. But then when you do the outside and the inside, those are going to cancel because one of them is going to be minus 8i and the other is going to be plus 8i. So I'm not even going to bother writing those because they cancel. So it's just the last times the last, the negative 2i times the 2i, that you'll get minus 4i squared. But then the I squared becomes negative 1, so it becomes real. So it's really just 16 plus 4, so 20 in the denominator, right? So it's the top part where you are going to have stuff most of the time that has 4 terms, right? So 17 times negative 4 is negative 68. 17 times 2i is plus 34i. Negative 3 times negative 4 is positive 12i. And then negative 3 times 2 is minus 6. I times I is I squared. Right? And then you'll just need to combine together the imaginaries. 34 plus 12 is 46i. And then this right here is going to be real. That can go together with this guy, which is real. Because this is ultimately really the same thing as positive 6, because I squared is negative 1. So negative 68 plus 6 is going to be negative 62. And then you'll just need to split that in a couple separate fractions as negative 62 twentieths and 46 twentieths I, and then reduce the fractions as far as you can. So the first one is just going to come out to be negative 31 tenths. The next one will come out to be 23 tenths times I, and then that would be your quotient in simplest possible form there.